All right, let's connect the exterior product, the interior product, and the cross product. The one extra tool I want to recall is the Hodge star operator. And what that does is it exchanges one forms and two forms. That's how it works in 3 dimensions. In n dimensions, it exchanges p forms with n minus p forms. Basically, it flips the whole structure upside down. In fact, 0 forms and 3 forms exchange with each other, although we won't need that right now, and 1 forms and 2 forms exchange with each other. And it's very simple if you write everything out in terms of an orthonormal basis. Star dx is dy wedge dz, star dy is dz wedge dx, star dz is dx wedge dy. And this encodes the fact that 1 forms and 2 forms in 3 dimensions have the same amount of information. What's going on here is, to use the fancier terminology, is that these are isomorphic spaces. They have the same amount of information, and you can have a mapping that goes back and forth between them. So this is what dx what it does from 1 forms to 2 forms. Turns out in odd dimensions, it's very easy to tell you what the star does from a 2 form to 1 form. It just goes backwards. In fact, so star is really its own inverse. When you do it twice, you get back to exactly the same. That's special to odd dimensions, as it turns out. So, in particular, if I have A, which is a vector, we already have a way of turning that into a 1 form, a tilde, which is just replace the e's with the dx, dy, dz. Now, I have to say, this, like the star, everything I'm doing now, the star and the tilde, very, very much depend on having the notion of dot product. And in fact, the star also depends on the notion of having an orientation. Like, what do you consider positive? And namely, that dx, dy, dz in that order is a positively oriented triple. And so given that structure, you can make this translation. If you change variables or do some sort of linear transformation that doesn't respect that isn't just a rotation, and that changes lengths and angles and dot product, this correspondence will change and will mess up. So that's actually rather important. But that's okay, because the cross product is intimately tied with the geometry in the sense of the dot product and the orientations, the right-hand rule. And so it's okay that we're depending on that structure now. So what the star allows us to do is not only to identify really 3 kinds of things as the same object, basically. Vectors, 1 forms, and 2 forms. And so we're going to be freely use those translations, and really this is going to be about how those translations work and how they allow us to do things like the triple vector product. Okay, so I want to note that this is also equal, I claim this is also equal to the interior product of A. Well, what would it be? To end up with a 2 form, it must start with a 3 form. In fact, it's just dv, which is just a nice abbreviation for dx wedge dy wedge dz, the volume form. So if you take the volume form and you interior product that with A, I claim you get this. Let me just show a bit of that, just not to be take too long. Let's just do the calculation for like I dx on dx wedge dy wedge dz. And just as an illustration of the derivation formula, which I want to focus on from now on in terms of the interior product, let's use that. So I'm going to consider this is alpha here, and this is beta, the dy dz as beta. And so I'm going to get that should be I E1. There we go. Okay. So I E1 dx, wedge the rest, and then minus dx wedge IE1 of dy wedge dz. Hopefully you can see that. Yeah, okay. Now I don't have enough room to finish it, but that's okay. Let's see. I want to save that. Okay. Let me take that up here. Well, IE1 dx, that's equal to 1. That's the pairing of the x, the first coordinate with the first vector. That's equal to 1, so I just get dy wedge dz. Minus, okay. Now IE1 of dy wedge dz, I can use it again. So this is dx wedge. Okay, so I get IE1 dy wedge dz minus dy wedge IE1 dz. Constantly using that derivation property. But the great thing is these guys just die. Okay, so this is sort of a sketch of a proof of the claim I made in the last video. Is it simply knowing how this guy acts on one forms and on numbers, scalars, and the derivation property, you can always recover what it does to anything. Okay, and so I just get dy wedge dz. Okay, so that makes it hopefully plausible. IE1 is just going to pick out the dy wedge dz here. I almost got it erased. Okay, A1 times E1 is going to give you an A1 dy wedge dz, and then the other components are just going to give you these guys as well. Okay, so it's what we would expect. Remember from the pictures, IE1, it picks out, it sort of it pairs with the dx but destroys it in the process and leaves the dy wedge dz. Okay, so this is going to be useful to know. Let me just erase the explicit calculation here and just remind ourselves that IA of dv is another way to think of turning a vector into a two form. Okay. All right. So now we connect to the cross product. Okay. And the sort of the punchline here is that there's two ways to connect the cross product to forms, and one of them ends up translating it to the wedge product, and the other one translating it into the interior product. And so this is one way to see that there's something deep going on with the triple vector product, is that we're going to interpret it in a way that the cross actually gets translated in two different ways. And that's kind of an interesting thing. Okay, and mainly it gives us a good workout with form algebra, really. Okay, so first is that if I take two vectors and I turn them into one forms, that's the simplest way to translate this all into form algebra. Okay, and then I wedge them together. Well, that's an antisymmetric combination of those two things. That's plausible that that would have to do with the cross product, and indeed, it does have to do with the cross product. But what's interesting, what's different from the cross product, is that these are both one forms, and the result is a two form. Okay, that's different. That something, this operation produces something that's the output is a different kind of thing. But we can deal with that. Okay, so what we would expect is that would be the same as if you take the cross product, that's a vector, and then do the star tilde. Turn that into a two form. Okay. So the key is that on the inputs we're using the tilde translation, the one form translation of vectors, and on the output we're using the two form translation. So the claim is that that's an equality. That's actually something I showed in another video, or at least alluded to in another video. And I'll just leave it for you guys to check. Just check it on IJK, or E1, E2, E3, however you want to call them. Or just really, if you can. It's pretty easy to notice that if the two vectors are the same, like E1 with E1, both sides are going to die. And then if you just check E1 and E2, it'll work. And then you can probably trust me that cyclic permutations are going to also work as well. Okay, so that's the first way. Okay, so this is number one. Okay, number two over here is that if I take A cross B, okay, well, what if I don't turn that into a two form? What if I turn it just into a one form? What if I turn the output into a one form instead of focusing on the inputs? Okay, well, it turns out, let's see, that's going to be a one form. It turns out to be the interior product of A with the two form version of B. So I take B, which is a vector, turn it into a two form with the combination of star and tilde, and then an interior product with A. That gets me back to a one form, and that's indeed what this guy is. Okay, so we've already had hints of this. When this was, if B is E3, then star E3 tilde is just dx dy wedge dy, and this is really the calculation of IA into dx wedge dy that we saw before. So that was actually a hint of this general calculation. Again, the easiest thing to do is just check it in components. It's really not hard to see. So here the perspective is that I turn one of the inputs into a two form. I leave the other one is a pure vector, not even turning it into a form. And then I have an operation that now turns that into a one form. Oh, okay. Turns out that's the one form version of the output. So it's a switch in terms of, do I think of the inputs as one forms, like here, or do I think of the output as a one form? That's the difference between these two versions. Okay. Now in the next video, I'll finally get to the punchline of this part, which is that are most, what I think is the most important identity about I, the interior product, will immediately give us the triple vector product identity.